In this video, we're going to look at Bohr model calculations and both qualitatively and quantitatively. So starting with the qualitative aspect of it, we should be able to answer this question. And you've seen this before, but I want to just point out that we're asking for emission here, so the difference in energy is going to be less than zero or negative, and that comes from the idea that the change in energy is equal to the final state minus the initial state. And if we look at our energy diagram here on the right, anything going from a low energy to a higher energy is going to result in a positive energy, and so, or absorption of energy. So that eliminates A and C from our answer options. The remaining three are emission of energy, and emission is, like I said, negative, so we're going to be going from high energy to a low energy. And we need to understand here that the difference in energy for these levels is equal to the energy of a photon emitted. And so the relationship between energy of a photon and wavelength is inversely proportional. Recall, the energy of a photon is equal to hc over lambda. And so we see that inverse relationship between wavelength and energy. So what we need is, if we're talking about a long wavelength, that would correspond to a small energy, or in this case, a small change in energy. So we want the transition that's going to result in the smallest change. What you have to keep in mind here is that the transition between n equals 1 to n equals 2, this energy of 1 to 2 is greater than the energy of 2 to infinity. So any transition involving energy level 1 is always going to be a larger magnitude than any other transitions possible. So that rules out D. 2 to 1 is going to be larger energy than any other transition there. So then we look at 6 to 2 for B, or 10 to 2. And 6 to 2 is going to be a smaller energy, and so that would be resulting in the longer wavelength. So that's how we can qualitatively arrive at this conclusion. Now let's think about calculating the energy involved from the 6 to 2 transition. On our data sheet, we have a version of the Rydberg equation, and that's shown here. And in that we have this RY unit, that's the Rydberg unit. It's equal to 2.18 times 10 to the minus 18 joules. And we can use this equation to plug our numbers into to calculate the change in energy for that transition. So 1 over, we're starting at the 6th energy level, and we're going to the 2nd energy level. So that would be this 2 squared, and plugging into our calculator, we will get negative 4.84 times 10 to the minus 19th joules. This negative sign indicates light is emitted, and that's what we're looking at, so that makes sense in terms of our check evaluate part. So that's the energy, and we know that delta E of the transition is equal to the energy of the photon emitted. So if we want to know wavelength, E equals hc over lambda, lambda is equal to hc over E. So we can solve 6.626 times 10 to the minus 34th joules seconds, that's Planck's constant, times the speed of light, and dividing that by the energy we calculated. The sign of the energy is not important here. We know that wavelength, and if we were even calculating frequency or something, cannot be negative. So we're going to leave that negative sign out. And this calculates to 4.10 times 10 to the negative 7th meters. And if we were going to convert that to nanometers, it would be 410 nanometers. That is in the visible spectrum, so we would expect to see a photon of violet light from that transition, and this is in fact one of the lines in the Balmer series of the hydrogen atom. Okay, thanks for watching. Let me know